just amounts to this row vector times this. So this 1 by 2 vector times this 2 by 3 vector, which gives me a, what is that? 1 by 3? 1 by 3. I don't know. I need to teach more linear algebra. I don't. You're right, I don't. I have too much linear algebra. No. I mean, it's not linear algebra this problem. It's 8:15. Like 8:15. It's just no time to do anything except sleep. It's time for sleeping. Oh, 8:15. All right, so as you can see, we've got this and that and that. These are the chain rules that we teach you in Calculus 3 by drawing those like tree diagrams and stuff. But rather than driving them from a tree diagram, I just got it from matrix multiplication. That dot that gives me this. This dot this gives me these two. This dot that gives me these two. These are the usual multivariate chain rules. What's so funny? About the what? Oh, her boyfriend. Oh, exciting. I don't know. I have no information about that, so I only know about Violet's boyfriend. Let's see here.
I don't have a boyfriend. Is he cute? He doesn't exist. Is he tall?
He's in the back row.
Oh no. I didn't say it. I didn't say it. So okay, so let's see here.
That's funny.
It's been a while since I created a good fictional relationship, so
I'm scared of my life.
yeah. Anyway, so here. All right, I think I was going to say the other thing that you can see the Jacobian matrix, perhaps you might recognize, and we'll talk more about this as it comes up later, but this is like this is polar coordinate change, right? See, this is Preston's fault. So this is polar coordinate change, right? And so
was that the
has anybody ever done that in Convo? No. Somebody should.
not yet?
Yeah. 10 bonus points, by the way, if you can document it. So I was never here. I never said it. But still, send me a clip. No one watches this. So this is the Jacobian matrix of the coordinate change, right? Partial x, partial r, partial x, partial, and then theta derivatives over here. You might recognize this. We took the determinant of this. We did this times that minus that times that. It gives us r times cosine squared plus sine squared. That gave us the r, which was in the coordinate change formulas at the end of Calculus 3. We called the Jacobian in Calculus 3 the determinant of the Jacobian matrix here. There's something called the multivariate coordinate change theorem where that comes up in, yeah.
I think you've got
Oh,
three
no.
Y's up there on top.
3 y's?
Yeah, the second line.
Oh.
No, it's just one part of the x got erased.
Huh. But I got the sine theta here.
No, it's totally an X because it's not looping.
Oh, okay. Well,
She's right.
I'm going to
She's right.
go on. So this is just a hard calculation. This has not much to do with what we're doing, but it's a fun calculation. So I couldn't bear to not include it because it's just a calculation I love. So, all right. So enough of that. I want to go back here and talk about another thing. Oh man. All right. So we talked about linearity of the derivative last time, and we talked about directional derivatives, right? We talked about these things. I'm trying to find something here. I'll find it eventually. So now we've talked about the Jacobian a bit. Now we can do more. If you want to see another example of it next time, we'll do it. I'll try to do another example. Next class, I'll try to find the linearization at the start of class or something. That'll probably help you guys see it again. But there's a caboodle of examples here, right? I asked you to find the differential of x dot y in the homework. So I think this is almost it. Maybe it's it. It's pretty close to the homework if it's not the homework. So anyway, there's a bunch of calculations here. And maybe we'll come back and look at some of these more. But what I wanted to talk about past... Where is this stupid thing? Man, it's been a little bit since I worked on this course first. I have 5 courses I'm teaching right now, right? This is one that's most near and dear to my heart. So I worked on this one first and created the insidious homework that you just suffered through months ago. But I do think it gets better, by the way. So this is the nature, like Calculus 1, the hardest part is actually at the start. If we actually study continuity there and study limits carefully, that stuff's difficult, right? It's really difficult to prove those things. And then it gets better. And I think the same is true for this course. At least that's what I'm hoping. So this is a theorem that I wanted to share with you guys. And I'd actually like to prove this one. But before I look at this, I wanted to show you what I'm talking about here. So check it out. These are some product rules of calculus. All right? Calculus 1, first place you see, product of 2 functions of reals, we have the product rule, right? df dt times g plus f dg dt. Of course, we usually use an x there, but you get the idea. The product rule, the plain old product rule. When you're talking about functions of n variables and you're taking partial derivatives, guess what? Still have a product rule. So partial derivative with respect to x of a product is partial f partial xi times g plus g, f times partial g partial xi. Another product rule. When we look at a product of a function times a vector, and here this vector is a function of, let's see here, so the domain for both the function and the vector valued function, these are both functions of n variables, so I can take the partial derivative with respect to the xi. And again, we have a product rule, but this time partial f partial xi times v plus f times partial v partial xi. It's good nobody's trying to teach in here or anything. Certainly no reason to, not blast the music over there. And then, of course, if we have a dot product of 2 vectors, right? And suppose that they're functions of time. So this could be like velocity and acceleration. You take the derivative of the dot product of acceleration and velocity, something like that. Then we have this product rule, the dot product, so it's like dv dt dot w plus v dot dw dt. If you have a cross product of 2 functions of time, there's a product rule. You have dv dt cross w plus v cross dw dt, right? A product rule. If you have... I swear. All right. If... I'm going to go do something to the audio video over there. And disable the speakers somehow or another. I just want to make them work, but quieter.
Just have every time, hack it so that every time they try to use the speakers, it's just never going to
I need to ooh. That's nice. I like that. So if we have a product of matrices, see, these are both matrices of functions, like we looked at a little bit last time, remember? I apologized for the lack of background for that. Well, if you have a product of functions of matrices, you have a product rule. The a dt times b plus a times dv dt. Now you have to keep track of the order of the matrices because matrix multiplication doesn't commute, but nevertheless, there is a product rule. And last, but certainly not least, well, I mean, maybe it's least, I don't know, but let's see here. Now I have a function of a complex variable, I think, x plus iy, and it's complex valued, I think. So it's got a real and an imaginary component function. If you have a product of such things, you have a product rule. I mean, if there is a product, there is a product rule. And so I used to have like 5, different proofs for all of these different product rules, and I found myself keep doing the same thing over and over again. So I decided to instead prove them all at once. Yes, the omega proof. So And this is more general than that. So let me explain what this proof means. All right? So I have different things going on. I have W1, W2, W3, and V, all finite dimensional real norm linear spaces. U is a subset of V. So I'm thinking of V basically as the domain of the functions involved. V is the domain. Well, U is a subset of V, which is U is the domain. So V is the place where the independent variables are. And I'm letting gamma 1 be a basis for W1, gamma 2 be a basis for W2, and I'm looking at some kind of product, which is to say it takes in something from W1, something from W2. It takes those two things, puts it together, and gives you something in W3. And that product has to satisfy these rules of algebra. Like it distributes across addition like this, and it distributes across addition like this. So these two together, taken together, we call this makes the product bilinear. It's linear in each entry, in the W1 entry and the W2 entry. If that's the case, and we have a function f which goes from U to W1 and a function g which goes from U to W2, then we can define f star g pointwise by this rule. F star g of a is equal to f of a star g of a. This could be the dot product, this could be the cross product, this could be the scalar product, this could be the matrix product, it could be all the products we just talked about. And if we do that, then the theorem says that the partial derivative of such a function is simply given by the product rule, where you take the star product between these. And by the way, the differential of such a function is actually the star product of the differential of f with g and f with the differential of g. This is true for all of the products I just looked at, and more. So like the proof over here is just this. It rests on, first of all, noticing that if you have a product that has that bilinearity, what you can do is you can define it in terms of a characteristic set of numbers called structure constants. So basically I say basis for W1 times the basis for W2 has to be given by this like linear combination of the basis for W3. All right? And so if I then multiply f times g, I can use this formula to rewrite my formula for the product of the two functions in terms of this summation down here. So what we're looking at is numbers. These are all numbers, and that's a vector. So like these are the component functions of f star g. All right, these are the component functions of f star g. But if f and g are separately given to be continuously differentiable, which is the assumption in the theorem I just wrote, that means that the differential of this exists, and its differential is given by the partial derivatives of the component functions linearly combined, as I talked about at the start of class today. And so when I take the partial derivatives of this, what do? Well, here's what I do. So the elf partial derivative, I have this, but then notice that we have this sum, and the partial derivative is linear across the sum, so I can bring the sums out, and then I'm just getting the partial derivative of this. But these are just ordinary functions being multiplied. This is a real multiple of functions. So there, I just have the ordinary product rule from like calculus 1, essentially. And so that gives me the product rule. And then I just undo all the algebra I just did. I break it into two sums, and I undo the basis expansion, like here. These encode the multiplication. So I undo those by putting the star down here like that. And that's what I'm trying to prove. So this one calculation all at once proves all the product rules I just showed you, and more, because actually this product rule equally well applies to, say, calculus over an associative algebra, which has products which maybe you've never heard of, but it's anyway. So I'm proud of this product rule, but this is not the kind of thing I would test you on, right? Not directly anyway. So I don't think it's really interesting for me to make you memorize this proof and repeat it back to me, okay? There's other ones that I might, but not this one. So anyway, I think that's it for today. So next time we will look at further examples. I don't think I have anything to prove next time, so it should be just examples next time. So.